Hi there, this is Coach Suiso, and welcome to Lesson 2 of Chemical Reactions. This is going to be part 1 of Lesson 2. We're going to split the lesson into 2 parts. The first is going to be about classifying the types of chemical reactions, and the second part of Lesson 2 is going to be about writing chemical reactions, which is essentially translating from the chemical reaction to the word equation. We're going to have 5 basic reaction types that you are going to have to learn and memorize, and you'll have to recognize them and identify them. We're going to learn more about each one individually, but just to look at them as a whole, we're going to have synthesis, decomposition, single replacement. It's also known as single displacement. Either or is fine. Double replacement, also known as double displacement. Again, either or is fine. And combustion. So let's start with synthesis. Synthesis, also known as combination, is the combination of 2 or more substances to form a compound. It only has one product. So if we look at this visual example here, we've got element A, element B, and they combine to form one product, which is compound AB. If you look at it in a structural sense here with this chemical reaction, we've got 2 coppers, we've got 1 oxygen, and it combines to form 2 copper 2 oxides. And you notice here that even though we've got 2 different reactants, we have one product. The next type of reaction is decomposition, which you can think of as the opposite of synthesis. And I'm going to just jot that down here for you. So if synthesis was taking 2 or more reactants and making one product, decomposition is taking that one and breaking it down. So this time you've got 1 reactant, which here would be AB, and you break it down into 2 or more substances, which is your product. And again, remember, 2 or more is really important. It doesn't have to just be 2, it could be 3. So an example down here, we've got 2 water molecules, and we are breaking that down into hydrogen and oxygen. So we've got 1 reactant and 2 products, the opposite of synthesis. So that is synthesis and decomp. Those kind of go in a pair. Next, we have what's called single replacement. Single replacement occurs when a single element reacts with an ionic compound and switches places with one of the elements in the compound. So a better way of looking at it is you have an element and a compound, and you yield a different element and a different compound. So, for example, if I've got compound BC, and here it is visually, and I've got element A. A is going to come and boot out one of the elements from compound BC. So in this case, it booted out the B. Now B is by itself over here, and you have new compound AC. It's important to note that this has to be an ionic compound because ionic compounds, remember, are not really bonded. They're simply attracted to each other because of their charges. You cannot do this with a covalent compound. But most of what we're going to be working with in this particular unit when we deal with compounds are ionic anyway, so you don't really have to worry too much about that. There's 2 types of single replacements that you can have. You can have cation displacement or anion displacement. So if you've got cation displacement, that means that the element that's by itself, that's going to be booting out one of the elements, is a cation, which means when it boots out one of the elements in my ionic compound, it has to boot out the other cation. Anion displacement is the opposite. The element that's by itself is an anion. So when it boots out an element, it's got to boot out the other anion. Because remember, an ionic compound has to have both a cation and an anion. So when that element takes a place of another element in that compound, it has to take the place of the one with the same charge. So in cation displacement here, we've got this aluminum. It's going to boot out the copper because aluminum and copper are both metals. And you're going to be left with copper on its own and your new compound, which is aluminum chloride. When you have anion displacement, chlorine is a nonmetal, so it's got to boot out the other nonmetal, which in this case is bromine. So you're left with a new compound, which is potassium chloride, and then your element by itself now is the bromine. Remember, this is also a really good opportunity to remind you to review your balancing. Every single time you have an equation, you've got to make sure that it's balanced. So let's check both of these to see if they're balanced. This kind of reviews what we talked about in lesson 1. So I'm going to erase my work here so we can see this clearly. Let's look at the first one. We've got 1 aluminum, 1 aluminum, 1 copper, 1 copper, 2 chlorines, and 3 chlorines. So that is mismatched. We don't have the same number of chlorines on both my product and my reactant side. So on the left-hand side, I'm going to put a 3 here to make that 6 chlorines. And on this side, I'm going to put my 2 here to make that 6 chlorines. Now I've messed with my aluminum and my copper, so I need to put a 2 for the aluminum here and a 3 for my copper here, and I am balanced. This anion displacement is also unbalanced. Let's check it out. We've got 2 chlorines on the reactant side, and on the right-hand side, we have 1 chlorine. So immediately right off the bat, we know we're going to have to adjust that. So I'm going to put a 2 right here. Then we've got 1 potassium on the left-hand side, and because I've added that coefficient there, now I have 2 potassiums on the right-hand side. So what do I have to do? I need to go back and put a 2 right there. Now, let's check my last element here. I've got 2 bromines because of that coefficient, and on this side, I've got 2 bromines because of this subscript. So I am balanced. All right, the next type of reaction is a double replacement reaction. This is 2 compounds change partners. So you're always going to have 2 compounds in your reactants, and you're always going to have 2 different compounds in your products. The cation of one of the compounds is going to combine with the anion of another. So this is like if you've ever seen the TV show like Celebrity Wife Swap, etc. It's like that kind of concept, right? You're swapping either the cations or the anions. So my example here, I've got compound AB combining with compound CD. So A and C are my cations, so those would swap. Or you could think of it as B and D, my anion swapping. You can pick whichever one you want to swap. And then we get our new compounds, which is AD and CB. So if you look at it visually right here, we've got compound AB and the A and the C swapped. So now A is with D and C is with B. What to look for when you're identifying this is 2 compounds on the reactant side and 2 compounds on the product side. And each compound always has to remember have a cation and an anion. They're always ionic. There is a very specific type of double replacement reaction. It's called an acid-base reaction, or what we call neutralization reaction. It's very specific. It's when you've got an acid and a base, and they react to form an ionic compound, which is a salt and water. It's how you neutralize any acid or base. So, for example, if I've got HCl, which is hydrochloric acid, and I combine it with sodium hydroxide, which is a base, then if I swap my anions and my cations, I'm swapping my hydrogen with my sodium here, swap my cations. I now end up with a product of NaCl, which is a salt. And then I end up with H and OH, right? That is my, let me do it in a different color for you. That is my cation and my anion from those 2 compounds is HOH. But we don't ever write HOH like that. We simply write it as H2O. So that is water. Another example of this, same exact process. We've got sulfuric acid, which is H2SO4 right here, and we're combining it with 2 moles of potassium hydroxide. So my sulfuric acid is my acid, and that potassium hydroxide is my base. And remember, I'm going to swap my cations. So now my potassium is going to be with my sulfate to make potassium sulfate, which is a salt. And then my hydrogen is now going to be with my hydroxide, which is really just water. So it's the same exact thing as the other double replacement reactions, right? You start with 2 compounds, you end with 2 compounds. So you're looking for the same thing. That buzzword, that red flag to tell you it's double replacement doesn't change. The only thing that's a little different about this is that HOH just gets written as H2O. Finally, the last type of reaction is going to be a combustion reaction. A combustion reaction by definition is a rapidly occurring reaction with oxygen that involves light and heat. And it occurs when you have a hydrocarbon, and that reacts with the oxygen to produce both water and carbon dioxide. A hydrocarbon is a compound that has only carbon, hydrogen, and sometimes oxygen. If you study organic chemistry in college, you'll do a lot with hydrocarbons. In fact, you'll primarily work with them for an entire year. But hydrocarbons are going to react with the oxygens, And every single time they are going to produce carbon dioxide and water. So when you're looking to identify a combustion reaction within a group of different types of reactions, it's always exactly the same. The only thing that's going to change about it is what hydrocarbon. You could have butane, you could have methane, you could have any hydrocarbon, but it's always going to be reacting with an oxygen, form carbon dioxide, and form water. So that will never change. There are some other instances where combustion happens without a hydrocarbon. So for example, we did this actually, or we've done this previously on like the first day of school and some labs where you take magnesium and you put it in the presence of heat and it reacts with oxygen to form a really, really bright light. That is combustion, okay? So you do have some combustion reactions without the O2, without the CO2 and all of that. However, in our class, we are going to classify combustion as reacting with a hydrocarbon with carbon dioxide and water every single time. So I would star that, circle that, highlight that. This particular example right here is just as an FYI, so that if you see that in scientific literature or in your textbook or any other place that you might be looking at combustion reactions, that would classify as combustion scientifically. But for the primary purpose of this class, we will not worry about that as combustion. Combustion will always look like this right here. Always, always, always for us, okay? All right, so let's look at these right here. We've got 5 examples. Let's go ahead and take a minute. We can pause the video and let's see if we can identify each of these types of reactions. And while you're at it, also make sure that they are balanced. You always want to check, because some of them might be balanced, but some of them might not, and you never want to take that for granted. So go ahead and pause the video for a second and identify each of these with which type of reaction they are, and then I will go through them. Okay, so let's go through each one here. At the beginning, the first one, we've got H2, hydrogen combining with chlorine to form 2 HCl. So if you're looking for kind of red flags to help you identify it, you've got 2 reactants and it forms 1 product. So this is synthesis. And let's check our balancing. We've got 2 hydrogens, 2 hydrogens, 2 chlorines, 2 chlorines. It's balanced. So that one's all good. Looking at the second one, we've got an element and a compound. And on the other side, we have a new compound and a new element by itself. So this copper took the place of the silver, and now silver's alone on the product side. So this is single replacement. And remember, you can also call this single displacement. That's completely fine. You'd get full credit for that. Let's check our balancing. We have 1 copper, 1 copper, 2 silvers, 2 silvers, 2 nitrates, 2 nitrates. We are balanced. The third one, we've got a compound. We've got lead 2 nitrate here. Then we've got potassium chromate. And on the other side, we have 2 other compounds, lead 2 chromate, and potassium nitrate. So this is 2 compounds forming 2 new compounds. This is double replacement. And remember, you can also call this double displacement. Either word is correct. Let's check our balancing here. We've got 1 lead, 2 nitrates, because see that number at the front, that coefficient affects those nitrates. We've got 2 potassiums here, 2 potassiums here, 1 chromate, 1 chromate. We are balanced. All right, this next one, we've got a compound here. We've got potassium chlorate. And that potassium chlorate is going to break down into potassium chloride and oxygen. So we've got 1 reactant breaking down into 2 or more products. This is decomposition. And we are balanced. We've got 6 oxygens, 2 chlorines, 2 chlorines, 2 potassiums, 2 potassiums, and 2 chlorines. All right, this last one, immediately upon seeing it, you should recognize that we've got an oxygen reacting with a hydrocarbon to form carbon dioxide and water. So immediately, your first thought should be that that is combustion. Now this one is not balanced. So let's go ahead and review balancing for combustion. This was that last example that I did on lesson 1. So this is the one with the trick where you want to leave the oxygen for the end and double it if you need to. Remember, all combustion reactions can be solved using this technique. So let's start with our carbon. We have 3 carbons on the left, 1 carbon on the right. So I'm going to put a 3 right here. Then we've got 7 hydrogens here, and then 1 here. So we have 8 total hydrogens on this side. And on this side, we've got 2. So I need to put a 4 right here. So now we have 8 on each side. Now let's look at oxygen. We've got 1 oxygen here and 2 oxygens here. So that's 3 total oxygens on this side. And on the right-hand side, I've got 3 times 2, which is 6 plus 4. So I have 10 oxygens over here. Now I've got a little bit of a problem because on the left-hand side, I don't just have oxygen in one spot. I've got oxygen in 2 in that hydrocarbon and then also independently in that oxygen atom. So what I'm going to do is actually take away that 1 oxygen right here and just say I've got 2 oxygens on this side plus 1. So whatever I multiply this oxygen by, it's got to get to 9. Because if it gets to 9, then I add this 1, and then I've got the 10 that matches the other side. So what times 2 equals 9? Well, it's 4.5. So like I did on that one yesterday, let's erase all my chicken scratch here. That is technically balanced, right? I've got 4.5 times 2, which is 9, 10 oxygens. And on this side, I've got 6, 7, 8, 9, 10 oxygens. But can I leave a 4.5? No. Remember, you have to have whole numbers for your coefficients. So my last step is to multiply across as needed. So this would be 2, 9, 6, and 8. And now we are balanced. That's about as challenging as a balancing equation can possibly get because you've got that double thing that you need to do with the 4.5, but you also have oxygens in 2 spots on the reactant side, which makes it a little bit more challenging, but not impossible if you just follow the steps every single time. All right, that concludes part 1 of lesson 2. Go ahead and watch the second video, which is on writing equations to complete the lesson 2 notes.